so bad at that. My gosh. Okay. Okay, so I missed a lot today. Wow. Okay, so what else do we know? Ezra, what's the other thing we know?
We know initial velocity.
Is what?
Zero.
How do we know that?
It comes from rest.
Comes from rest. Okay, good. So V0 is 0, and what is it on this one that, Brady, that we're trying to find? We're supposed to find time. Good. Okay. So what equation are we going to use here, Elijah?
Final velocity equals initial velocity plus acceleration.
2. There we go. How about that? Equation 2. Very good. Okay, so in this case, we're using equation 2, but what is it that we're trying to solve for? T. Okay, so we have a choice. We could either plug numbers in first and then solve, for T, or my preference, solve for T first when you have nice clean variables in there, right? And then I think it makes it a little easier. So we have the equation V equals, now what's V naught? 0, so we don't even have to include that one, do we? Right, V naught is 0, so we can even just leave it out of the equation. So in this case, V just equals AT. What's the only thing I have to do to get T by itself? Yeah. So in other words, we can just rewrite the equation. T, if I just divide both sides by A, right, we just get T equals V over A, right? Okay. And what's that give us? So V is 28, A is 5.5, and that's roughly equal to I just remember that from last period, so it's 5.1 seconds. Okay, rounded to one place, 2 places. Make sense? Okay, questions? Okay. All right, so let's see, number 26. 26. Okay, so 26, we've got, if a car accelerates from rest, car slows from 22 meters per second to 3 meters per second at a constant rate of 2.1 meters per second squared. How many seconds are required before the car is traveling at 2 meters, or at 3 meters per second? Okay, Nathan, give me something I know about 26, please.
The initial velocity is 22 meters.
Okay, very good. So initial velocity, 22 meters per second. Michelle, give me something else.
The acceleration, the acceleration or the deceleration is 2.1 meters per second.
Okay,
Negative
so
2.1 meters per second.
So yeah, okay, good. So we always want the acceleration, and it's negative. Good. Negative 2.1 meters per second squared, right? Okay. Going back here, Nathan, give me something else. We got initial velocity, acceleration. What else do we know?
The final velocity.
Final velocity. Yeah, sure. Okay, we know final velocity, don't we? So final velocity is 3.0. And what is it that we're trying to find, Elijah, in this one?
Time.
Trying to find time, okay? Okay, so what's going to be the equation we're going to use, Brady, for this one then? This is the stuff we know, that's what we're trying to find, that matches the information in which equation?
V equals V naught plus acceleration times
Good. We'll call it equation 2. Good. So that's where we'll start. Okay, so. Trying to find T. So this time, Ezra, what are the steps we have to go through to solve for T this time?
We would,
In order.
we would subtract both sides by V naught.
Okay, subtract V naught and then divide by A, right? So if we do that, would you agree if we do that, we're gonna get T by itself. On the other side, we have V minus V naught, all divided by, right? We're dividing the whole side by A, and that's what we get, right? So now we can just plug and chug. So what do we get if we plug and chug? So V is 3.0 minus 22, right? All divided by negative 2.1. So that gives us, what? Somebody, the two places. What is it again? 9.0. And the units would be seconds. Good. Very good. Okay, make sense? All right, so moving on. Oh, that was it, wasn't it, for that one? Okay, so those would be worth, we said, oh, what did I do last period? Darn it, I should have remembered this. I think I wrote it down. Why am I such a dummy? How did I do that stuff? Okay, I'm pretty sure somehow it added up to 10. Does that make sense? How would I have gotten 10 out of that? I think I got 12. I think we made it 2 points. Oh, I know why. Because 23 only had two parts, so it was 10. Yeah. So 23 had 2 points apiece for a total of 4. 24, 25, and 26 were each worth 2 for a total of 10. How about that?
We only did 24.
We didn't do 24.
So that's
Oh.
18.
Oh, yeah, you're right. You're right. Okay, I guess it's worth 8. Fair enough. Okay. And on to page 103. Okay, so now we gotta add some equations, some more equations. Now, after this, we're gonna have all 4 kinematics. That's all we need. So the third equation, the way people typically list these, and there's a little bit of method to their madness, they typically list the 3 equations that involve time first, and then you get the non-time one. So the other one I called the Big Daddy. It's got the most terms in it. This is displace or position equals what? Okay, good. D naught. So initial position plus good initial velocity times time plus 1/2 acceleration times the square of time. Very good. Okay. So there's the Big Daddy. And then we've got number 4, which is very useful. Now, the way the book writes this is a little different. I'll tell you what I'll do. Maybe this would be helpful. Let me begin to compile a list of useful physics equations, which I will put on the Moodle site. The list right now really will only have, all we've really got is just kinematics equations, but we'll be adding some other stuff later. And so I will have those, I'll put it on there as a PDF, so you can just print it out or just pull it up whenever you need to. It might be handy, right? Just for now, just have these 4 things. The last one, here's how I think you should write it. I think you should write it as v squared minus v naught squared equals 2a delta d. Okay, make sense? Okay, make sense?
So what would you use that one to find?
Okay, so that one's useful when you don't have time. Just notice that's the one where there's no t. Okay. Keep in mind though, remember I mentioned to you earlier on this one that the v's, are they velocities? They're speeds, right? Because they're being squared, so they always appear as being positive, right? Okay, so there's our 4 kinematics equations, and now we'll be using more of those, right? Honestly, I don't think these book assignments are very good. They don't use a wide variety of these equations, but the Moodle one it'll make you use more of the equations. So 27, a race car traveling at 44 meters per second slows at a constant rate to a velocity of 22 meters per second over 11 seconds. How far does it move during this time interval? Okay, so I think we left off with TJ. Tell me something I know about 27.
Usually driving at 44 meters a second.
Okay, so V naught is 44 meters per second. Alexis, something else I know?
The final velocity is 22 meters per second.
Good. Something else I know, Nicole? Time? What was it again? 11 seconds. Okay, was that 11? Are these, how many sig figs on these? 2? Yeah, there we go. And while you're at it, what are we looking for? Nicole, what are we looking for while I'm stuck on you? Say it again? Displacement, okay, good. Now, okay, displacement, so let's talk about this very briefly. So we are looking for displacement. We want to know how far it went. What could we say that the initial position is here? They don't really specify.
0.
But why not let it be 0? Does that make sense when we say that? Because we get to choose. They don't tell us what it is. We're just going to arbitrarily say we're going to start this thing at 0. And that way, if we do that, if we let the initial position equal 0, what really is displacement then? It is change, right? It's defined as final position minus initial position, but the initial position in this case is 0, right? So really, would you agree that it's convenient to do this? Then we'll just say that displacement is really just final position, means we're starting from 0. You see what I'm saying there? It's not a big deal, but it's something just, don't get confused by that. I mean, that's something just to kind of file away a little bit. So then now this is one where we're going to do a little bit of thinking about. What's going to be the best way to approach this? There are multiple ways we could do these problems, and that's going to be the case for most kinematics equations, or most kinematics problems. We could probably use just about, I mean, we could fill in all the blanks here if we wanted to. We could determine what are all the things that were not given, and then eventually be able to use just about any of those equations, right? But what's the one that's going to be the easiest? What do you think, Deshaun? What's your opinion on that?
You find the average velocity and then multiply by time.
Yep, perfect. Right. This one is a really handy one to use when you can, right? Average velocity. Now, keep in mind that in real physics, in calculus-based physics, that first one is marginally useful because it only works for constant acceleration, right? But that's, everything we do in here is going to involve a constant acceleration. So for us, it's fair game, right? But that's a really useful one. We could take, what is, given the initial velocity and the final velocity that we have in this situation, what is the average velocity? Yeah, and you don't even really, you can just do it in your head, can't you? I mean, really, it's just the middle value. What's halfway between 44 and 22? 33, right? Yeah. And you can, if you want to, take an average, add them up and divide by 2, right? But we see right away that V bar is just 33 meters per second. Remember, bar means average, right? Okay. So V bar is 33. That first equation becomes awfully useful then, doesn't it? Right? So the first equation, if we write that down, position equals, what did we say initial position was?
0.
So just forget it, we don't even have to write it. V bar t. So it's simple. What's all we have to do to solve for t? Yeah, divide both sides by V bar. They cancel, and so t equals final position over average velocity, which is, oh, we're fine. Oh, never mind. Were we given Oh, we're finding D, never mind.
Yeah.
So, what am I doing? We don't have to do any algebra. We can just plug and chug. So then we just get D equals 0, we can leave that off, times 33 standard units, meters per second, times 11 standard units, so 363. What are the standard units of position? 363 meters, right?
That's
Makes sense?
too significant.
Oh, you're right, two significant figures. And so what would that be? 360, good. Very good, okay? Could we have done it a different way? Sure. I mean, we could have calculated an acceleration, I guess, right? Because we know initial velocity and final velocity and time, so we could have used equation 2 and found acceleration. And then once we have acceleration, we could have used really either equations 3 or 4, right? But why? Why do that? Doesn't make any sense in this case. I mean, really, it's just a lot more work. Make sense though? Okay? All right, so there's 27. And I think we just said on those 2 points apiece. Yeah, so just while we're going through, you can grade them. So that's 2 points. 28. A car accelerates at a constant rate from 15 meters to 25 meters per second while it travels 125 meters. How long does it take to achieve that speed? Okay. So, Sid, what's one thing we know?
Initial velocity is 15.
Good. Something else we know, going back, Sid, again, what's something else we know?
Final velocity is 25.
Okay, Deshaun, what's something else we know?
The initial is 15.
Okay, got that? Final's 25.
The initial is 0.
Okay, so we could
Final
say,
25.
good, we could say the initial position is 0, then what's that make the final position?
125.
Good, 125, okay. And what is it that we are trying to find, Nicole? Time. So what's the equation then that we're going to use on this one? What do you think, Nicole? What in your opinion, what are we gonna do here? Number 4? Okay, we could do number 4, but if we're gonna do number 4, what else do we need? Okay, either 4 or 3. Notice both of those, we don't have an acceleration yet, do we? Right? So we could, that's fine. We could use those, but we'd have to calculate an acceleration first, wouldn't we? Right? Okay, is there one we could use without, oh, hang on, am I doing the right?
Number 1.
Yeah, okay, yeah, we're good, yeah. Right, I sometimes I lose track of what I'm doing up here just a second ago. So does it make sense then that number 1 would be probably the easiest way? Now, that would work. We could calculate acceleration, and if we had acceleration, then we could use number 3, I guess, or we could use number 2, couldn't we, for that matter, right? Right, if we had acceleration, then that'd be a pretty easy one to use, right? So that, I mean, that's not bad. It wouldn't be that hard to do. But number 1 we can use right out of the hopper. What's the average velocity? Oops, oh my God. What's the average velocity? Halfway between 15 and 25? 20. So then that's pretty simple. We know the initial velocity or initial position is 0. So we have the equation final position, v naught 0, leave it out, equals v bar t. Now this time we are solving for t, right? So what's the one thing we have to do? Yeah, good. Divide both sides by v bar. So we get t then is approximately equal to 125, right? Divided by V bar is 20, so that's gonna be about 6.25, isn't it? Okay, so to how many places? 2, so 6.3. What are the units gonna be? Seconds. Okay, 2 points. Okay.
If you do the significant digits, are you maxing the point?
No, I mean, on these,
Okay.
I don't care. Just be on Moodle that you will get them wrong.
Okay.
Okay. On these, we're just focusing on the kinematics. I won't worry about it. 29, right? Okay. A bike rider accelerates constantly to a velocity of 7.5 meters per second during 4.5 seconds. The bike's displacement during the acceleration was 19 meters. What was the initial velocity? Okay. So, Alexis, tell me something that I know about 29.
Well, so the initial velocity is 0 and then its final is 7.5.
Okay, good. So we know initial velocity is what?
Oh wait, no, just kidding. It's asking for that. So
Okay, so
the
that's-
final is 7.5.
Okay, so that's what we're looking for. Okay, good. Final velocity you said was, what was it again?
7.5.
Okay. Something else, TJ, that we know?
We know that it speeds up to this in 4.5 seconds.
Okay, so we know t equals 4.5 seconds. While we're on you, TJ, something else?
It travels 19 meters.
Okay, so tell me a way to say that then. Tell me what I can write down.
It travels a distance of 19 meters starting at 0.
Okay, so we'll say d naught is 0. Okay, so we could, if it travels a distance of 19 meters, that tells us, we could write it this way. D naught is 0 and d final is 19. Okay, say another way would just be displacement is 19. That would include both, right? Okay, so what are we trying to find? What are we trying to find? Initial velocity, oh, we already have that. Okay, so what's going to be the equation here? This is a little trickier, maybe. What's probably the equation? Ezra, you have an idea? You could. We could still use number 1, couldn't we? Because what is initial velocity? What is average velocity?
The mean of the two velocities.
Okay, meaning it's the sum of the two divided by 2, right? Okay, so then if let's write this symbolically to begin with. So we could say then that d equals, d naught is 0, so we'll leave that part off, right? Equals average velocity. Well, if we write it as an average, it's just v naught plus v divided by 2, right? Times t. Okay, so this is a little more algebra this time. That's okay, right? We can do this. Now, if we're trying to, let me remind you real quickly how we solve for a variable. Whenever, this is just a PEMDAS thing, right? This is an order of operations thing. So if we write PEMDAS appropriately, so we're going to write it like this. PE and then the MD go together, right? Because they're on the same level. The addition and subtraction are together, right? And we just go bottoms up to isolate. And we reverse the order. So what are going to be the steps then? Now keep in mind, just a quick review here for, if you haven't seen this stuff in a while perhaps, we don't get to parentheses till the top, do we? So first we're going to undo addition and subtraction outside of parentheses, then we undo multiplication, division outside of parentheses. We undo any exponents, which would include roots, outside of parentheses, and finally we get to parentheses and start over again in the parentheses, right? So outside of parentheses, there's really only one thing to do here, isn't there? What's that? Divided by t. Okay, so the first step then is dividing by t would really be the same thing as just multiplying by 1 over t, but we'll just do it this way. So if we divide both sides by t, those go away, right? So I get a t over there. Okay, now we got rid of the t, and so now we can start in the parentheses. So at that point, let me write this down. So at that point, we've got d over t equals v naught plus V over 2. So now what, on this side, if we're trying to isolate V naught, what's the next thing? Multiply by 2, and then subtract V. Good, so would you agree then, if we do all that stuff, we're just gonna get D over T times 2. So if I multiply by 2, I can put that on top or out front, doesn't matter, right? Either way, I'll put it out front. Does that seem easier? I don't know, that seems easier. Either way. Either way, so there's the 2. Oh, that's bad too. And then all we have to do is subtract V, and we're left with our V naught all by itself, right? Plug and chug. So what's that give us? 2 times, I remember what were our quantities here? So we had 19 over 4.5 minus 7.5? Yeah. So what's that equal if we do all that stuff? 38 divided by 4.5. I don't really feel like thinking about that too hard. Somebody just want to tell me what it is?
0.95, or 94.5.
0.94. And what would the units be? Meters per second. Questions? Okay. If you would prefer, you can just plug the numbers in. If you'd rather do the algebra with the numbers, it's up to you. I don't really care. I recommend this way, but I will allow some personal discretion. How's that sound? So that's worth 2. Last one. Oh my gosh. How did this take so long? I really wanted to give you a good puzzler for the weekend. I don't know if I'm at time now. It's really disturbing me. That's true. We'll see if we have time here. So last one, number 30. An airplane starts from rest and accelerates at a constant 3 meters per second squared. We're just gonna zip through this one, how about? So they give us acceleration, right? 3.00 meters per second squared. They give us t is 30 seconds. And they give us something else, 30.0 seconds. They give us something else in a sneaky way. What's that?
The initial
Yeah, what's the initial velocity?
0.
0, because it's starting from rest. And we want to know, first of all, how far did it move? Okay, what could we assume that the initial position was? 0. And we're looking for then final position. Okay, so what's the one that we'd use? This is a little different one. Number 3, isn't it? Everybody see that? The stuff that we're given and that we're trying to find matches number 3, doesn't it? Right? So then, and it works out pretty well because it's already isolated. We already have the variable isolated that we're trying to find. So we can just straight plug and chug in that equation. So we just get D equals, D naught is 0, plus V naught is 0. So those both go away. We can forget them. The only term that survives is really just that last one. All the other ones are just 0. So it equals 1/2 times 3.00 times 30.0 squared. So we get 1.5 times 900 is 1350, right? What are the units going to be? Meters. Okay, make sense? Second part, how fast was it going when it took off? Okay, well, that's a pretty easy one, isn't it? Because what equation could we use to answer that one? Number 2. That's a little guy, right? Number 2 would be pretty easy. So V equals, and it's already solved for V, so we just plug in what we know, 0, right? Plus A, which is 3.00 times time, which is 30.0, so 90 meters per second. And we got it. So 2 points apiece for each part of number total of 10, and hang on to them, because I'm not gonna have time to collect them today, and we'll get them on Monday.